We are continuing our study of chapter 5.5.2. This is Mrs. McInnes, and we have learned how to do the fundamental theorem of calculus using U substitution with both indefinite and definite integrals. And today I'm just going to show you 3 shortcuts that are available for you to use. So the first 2 shortcuts have to do with the fact that when you are working with an even function, you have a graph that is symmetrical with respect to the y-axis. And then the second option is when you have a function that is an odd function where the function evaluated at negative x is the opposite of the function at f of x. And so let me go ahead and show you the very first example. So this is the integral from -2 to 2 of x to the 6th plus 1. We know we can integrate this, find my antiderivative, evaluate it 2, evaluate it -2, and subtract those. But I wanted to visually show you what we're finding. So this is x to the 6th, which looks like a parabola, and it's been shifted up 1. So you have some kind of shape that looks like this, and you are finding the area under the curve from -2 to 2. Well, when you have an even function like this, where you know that it is symmetrical with respect to the y-axis, the area on the left side and the area on the right side are the same. So another option is you could just focus on finding the area on the right side and double it. And that's what this first shortcut says. When you have a function that is even and you are going from -a to a, so a symmetrical distance from the left to the right, you can change your integral to an integral from 0 to a instead and double it. And you might be thinking, well, that doesn't save me too much time because I still have to apply the fundamental theorem of calculus. That's true, except that evaluating integrals with 0 almost always saves you some time. So the way we would set this up, instead of going from -2 to 2, I'd go from 0 to 2, and I would be doubling my answer because 0 to 2 will cover this area over here. And bring down my function. And now I evaluate my antiderivative of my integral. So my x to the 6th plus 1 becomes x to the 7th over 7 plus 1x. I meant to make that a bracket there. And we are evaluating from 0 to 2. So we have 2 to the 7th over 7 plus 2 minus 0 to the 7th over 7 plus 0. And so that's kind of the advantage, is that when you evaluate integrals with 0, it just zeroes out a large portion of your problem. So we've got 2 to the 7th divided by 7 plus 2, and we're going to multiply that whole thing by 2, and we get 40.571 for my area. So that is our shortcut when you're working with an even function. So our shortcut when you're working with an odd function, now it might not be recognizable right off the bat as this shortcut, because the shortcut requires that you also have your limits as opposite numbers, just like on the even function shortcut, -a to a. And that's not what we have here. So if I were working this problem, my natural way to start off would be to recognize that there's a function within a function. So I'm going to use U substitution. And I'm going to identify x minus 1 as my u. So du dx equals 1 dx dx multiplied by dx. So du is equal to dx. So I'm going to make these 2 substitutions here. So my integral carries down. I'm going to change my limits in just a moment. My x minus 1 really gets replaced with a u and bring down my 25th power. My dx now gets replaced with a du, and I'm going to change my limits over. So when x equals 2, u equals 2 minus 1, which is 1. And when x equals 0, which is my lower limit, u equals 0 minus 1, which is -1. And sure enough, now I've got u to the 25th power. That is an odd function. When you substitute in a negative u, you get the opposite of u to the 25th. You get negative u to the 25th. So that's an odd function, and I'm finding the area from -1 to 1. And I also want to look at this and consider what I'm finding visually. So u to the 25th, that's like a parent function very similar to u cubed. It's just going to be a lot steeper past 1 and beyond negative 1. So I have some kind of function that looks like this. And I'm finding the area from negative 1 to 1. Well, let's think about what we know. An odd function is symmetrical with respect to the origin. So if you were to take this upper right piece and reflect it over the y-axis and reflect it over the x-axis, it'd be sitting on it. It'd be sitting on itself. So these areas are in fact the same areas. However, this is a negative area and this is a positive area. So if we're summing up a negative area with its opposite area, the sum is actually going to be 0. And it saves you the trouble of having to actually integrate that function. So my solution would be 0 on that one. Okay, one last shortcut today, and this is really for our IB students. IB allows you to use a shortcut where we can bypass u substitution on the situations where your inner function is linear. Linear meaning y equals mx plus b. So in this case, ax plus b. So I'm going to use number 3 to kind of illustrate it. So I'm going to, if I were to integrate this, I know that I would be setting up my u substitution expression as ax plus b. And the derivative of u is du dx. Derivative of ax, a is taking the place of a number, so that would be a dx dx. And b is also a number, and this derivative would be 0. And when I multiply both sides by dx, those are gone. I'm going to divide through by an a. Remember, a would be a number. So now I have something to substitute u in for, the ax plus b, and I have something to replace dx with. So over here, this is going to give me u to the 7th power, and then this dx is replaced with du over a. And when I want to take my antiderivative, I see that there's a number here, and I'm going to pull that number out to the front. Now, it is in a denominator, so that's really equivalent to a 1 over a times the integral of u to the 7th du. So that 1 over a carries down. U to the 7th, I'm going to find my antiderivative, so that would be u to the 8th over 8. This is an indefinite integral, so I'm going to have a plus c on there. And then I can't forget that I've got to substitute my u expression back in. So we have ax plus b to the 8th power over 8 plus c. All right, so what is this shortcut we're going to use? Well, with every single u substitution problem where I'm working with a linear function, its derivative will always be that a value, which is essentially the slope. And when you substitute in for dx, the a always divides and becomes a denominator. So it will always become a constant in a denominator. So it will always become a constant out here in the form of 1 over a. And if you look at my original function, ax plus b to the 7, if I just reversed my power rule without substituting u in there, I'm bumping up my powers. So ax plus b to the 8th, there it is, divided by the power of 8. Now, you can't just reverse your power rule when you have stuff going on inside, but we're seeing now the only difference, the only thing we would be missing if we reversed our power rule right from the beginning is this 1 over a on the outside. So if you look over at our functions over to the side, when you have something in the form of ax plus b to the n power, it is the same as taking my a right here, 1 over a would be my coefficient in front, and then you raise that ax plus b to the n plus 1, so you bump up your power by 1 and you divide by that new power, and then don't forget your plus c. And that works with any other type of function that has a linear inner function. Ax plus b down there, ax plus b up here. So let's take a look at example number 4. Sine of ax plus b dx. So I'm not going to use u substitution. I'm realizing that that inner function is ax plus b. So I am going to take this constant number a, and I know my shortcut is I'm going to pull a 1 over a out to the front, and then I'm going to reverse my derivative. So sine is the derivative of a negative cosine. So negative cosine of ax plus b. Don't forget your plus c. And if you forgot that, it's right down here. Sine of ax plus b, your opposite would be negative cosine ax plus b, your antiderivative, excuse me. And I'm just going to clean that up and move the negative out to the front. So negative 1 over a cosine of ax plus b plus c. All right, let's look at one more example. So let's say you were taking example number 5. So I'm seeing that this is a linear function, 2x plus 3. So I'm going to take 1 over 2 to the outside, and I'm going to reverse my power rule. So I'm going to take 2x plus 3 to the 4th. I'm going to raise it to the 5th power. I am going to divide by 5, and then include my plus c at the end. So I'll just combine the 2 and the 5. So I have 1/10 times 2x plus 3 to the 5th power plus c. Let's look at one last example. So we've got sine of 7x minus cosine of 4x plus 5. This is especially helpful because if I was going to use u substitution, these would be different u expressions, and I would have to split this up into 2 separate integrals. But I'm not going to need to do that because I'm just going to use my shortcuts. So this is a 7x. So my coefficient of 7, that's going to come out to the front as a 1 over 7. Sine is the derivative of negative cosine. Bring down that 7x. Bring down that subtraction symbol. My inner function is 4x plus pi, so my coefficient of 4 would come out as a 1/4. The derivative, antiderivative of cosine would be sine of 4x plus pi. And then include your plus c on there. And you can just clean this up a little bit if you like. So now you've seen several different variations of using that shortcut, and IB allows you to use that on your test and avoid the u substitution process. If it's anything other than linear, if this were a 2x squared, if this were an ln of x, you cannot apply that shortcut unless the inner function is linear. All right, thank you so much for listening. Have a great day.